Hello, everyone, and welcome or welcome back, whichever the case may be. This collection of notes is going to be set up for Edgewood College's Math 610 on linear algebra. And so we're going to be reading this book. Can we see this book? Linear Algebra Done Right by Sheldon Axler. We're not going to be reading the whole book because it's a little bit too long for our 8-week sprint that we have for this module, but it'll cover, well, something of the book. And if you're in the class and not just a random internet stranger, then there's a good chance that you have already found our syllabus and you can see the order of operations, if you will, for the next 8 weeks. On the other hand, if you're just following along, that's fine too. We're going to just waste no time and just jump in. And we're going to start as one does at the beginning. Now, if you're coming from the previous class on abstract algebra, why abstract algebra comes first, the world may never know. But if you're coming from that class, then much of what I'll say in this video will probably be old hat to you, but that's fine. Let's just sort of make sure that we're all on the same page and start by introducing Euclidean spaces. Now, for our purposes, the Euclidean space means either Rn. Sorry, my drawing tablet is not working quite right. I think there's just some schmutz on it. Here we go. Rn or Cn. And what are these? These are going to be, by definition, tuples. Tuples here means lists of real or complex numbers. Now, a couple of things. I'm realizing that if I'm using the word list, that there's maybe already some confusion that's possible here. So we're gonna put a pin in this. Let's just go one thing at a time and try to clarify anything that we may not know here. First is some of you may not know what a complex number is. A complex number, z, we're gonna, you have x and y, which you often use for real numbers. We're gonna use letters like z for complex numbers. They will often be written in the form of a plus bi, where a and b are real numbers. And I is not a real number. It's a new imaginary number with the property that I squared is -1. With this terminology, complex numbers have a whole bunch of familiar looking properties, namely they can be added. We add their parts without the i's, and then we add the parts with the i's. Basically just like terms and all that. And they can be multiplied. The rule here is expand this. Sorry, that's not right. Or is it? Hold on. It was right. BC plus, that part was right. This part is wrong. Plus ADI plus BDI squared, right? Just doing algebra. And then using I squared equals -1. This I squared becomes a -1. We'll put it over with the real part. And then over here, we collected all of the stuff that is not real, so-called imaginary. So we will speak of this as the real part, the part without an I attached to it, and an imaginary part, a part with an I attached to it. Okay. For our purposes, we're going to be assuming a whole bunch of familiar things about complex arithmetic. I'm just going to write, you should know that these things are associative and commutative, and they have identity elements, namely 0 and 1, and they have inverses. You may have forgotten how the multiplicative inverse of a complex number works. I'm sure you know the additive inverse just by flipping the signs. but for a multiplicative inverse, what we do is we want to write this as 1 over a plus bi. In fact, that's completely reasonable. Then we multiply top and bottom by a minus bi and simplify the resulting thing. This gets me a squared plus b squared because difference of squares says it should be minus, but the I squareds make them plus again. And we get a over a squared plus b squared minus b over a squared plus b squared I. And then lastly, there is a distributive property. I'm just going to put it up here. Not going to make a big deal about it. Okay, so my suspicion is that the vast majority of you, if you found this playlist, you know all of this stuff already. And so I think we'll content ourselves for that part of the definition for what does Cn mean. Cn is comprised of complex numbers, and then we have to ask ourselves, what does the n mean? And this is what I started talking about regarding tuples or lists. So the classic examples that you know of this kind of stuff are things like R2 or R3, which have an x and a y coordinate, or maybe if you are fancy, an x, y, and z coordinate. To write this out properly, we should probably, use set notation like x, y, where x and y are real numbers. The crucial thing about this is that these are ordered. They have distinct first, second, or in this case, third entries. And I think that was why I sort of started wondering a little bit about whether or not the word list is a good term to use here. It is the term that Axler uses, so we can use it. Axler tells us that a list means, or rather a list of length n, means an ordered collection of exactly n elements. And so elements of this R2 are lists of length 2. Elements of this R3 are lists of length 3. And what kind of list are they? They're lists of real numbers. The reason that I was a little bit unhappy about this is because I think sometimes the word list suggests that the order does not matter. Like, for example, if you are going to the grocery store, your shopping list might be, eggs, milk, and cheese, or any other arrangement of those things. And it's the same list in the sense of you're still going to the store to buy the same stuff. For our purposes, though, our lists are going to be ordered, and these will be the prototypical examples. So the only thing that we haven't dealt with yet is just the complex part of this, which is that we are also justified in thinking about things like C3, which consists of, well, maybe I can use X, Y, and Z again, since I don't have too many other choices for letters, where each individual element is a complex number. So maybe we have something like 1i and 7 plus 4i as an example of a list of length 3 of complex numbers. Axler takes care to point out for us that lists and sets, they are different. And this is kind of what I was saying before, is in a set, your shopping list, the order doesn't matter. In fact, in a set, the repetition doesn't matter either. So you could have a set consisting of 2 duplicates, and it is exactly the same set as if it was the same. But we know for ordered pairs, these are different. I don't even know how you would write that. Maybe in parentheses, maybe just as a loose number. Doesn't matter. The point is, we'll need to take some care in our notation to separate lists from sets. Now, for going forward in this book, we will be oftentimes focusing on real or complex numbers specifically. we will often just write any so-called field. Those of you coming from the last class, you know what a field is. Can denote any field. But for us, often either R or C. However, if you know other fields, which maybe some of you are, at this point have some awareness of, it's a good idea to keep in mind that there are a lot of different fields out there, and maybe, and dare I even say, most of the results that I want to share with you in the next 8 weeks will make sense for any field, regardless of how the linear algebra that you have set up for that particular problem seems to shake out over a specific field. Oftentimes, it'll work in general from the right point of view. Let's see, any other notation that we need to introduce in this first video? We should probably talk about coordinates a little bit. So when we're talking about elements of a field or lists such as Fn, we will be able to speak of specific entries. We'll use subscripts when I have, a list of length n, right? Because I don't know how many n is, right? It's an arbitrary length. We'll use subscripts to index our variables. So if I want to speak of the ith coordinate, I'll probably just call that xi. And we will use this notation to mean lists of length n, elements coming from field F. Okay, and I think we are kind of close to ready to wrap up for this chapter. The videos that I want to be recording will be roughly following along with the book. I think there are some other things in this particular video that I think I'm just going to kind of skip over because I think we're kind of familiar with them, and you guys can just read it. But sometimes I'll have extra things that I'll want to include, either other examples I'll want to show, or problems that I'll want to work out. Problems may often get their own video. And as a general rule, I'm going to try not to skip over things without specifically calling your attention to that stuff or letting you know that you don't have to worry about this for the time being. So, for example, one of the things he spent some time talking about in this section are things like how are additive inverses defined, and addition being commutative and associative and so on. And all of this is cool and good. And if you haven't seen those things, you should take some time and look them over. Axler's book is written in no small part to serve as an introduction to the idea of proof itself. So for students who are rusty on those skills, or maybe have not ever had a class on mathematical proofs, it's in your interest to not do the kind of glossing over that I'm doing here. It's just, I don't want to read you this book. It's kind of a long book for an 8-week dash. And if I have to go through every single thing, well, half of you will be asleep. And if, on the other hand, if I don't, then half of you will have nothing to do. So it's in your interest to make sure that you really got all of these things before we just move on. But for the sake of expedience, well, I won't feel the need to say everything. I think that might be it. For this first section, there's some dozen problems or so. If you're in the class, there'll be homework that'll be posted following our usual format of I pick out some problems that you should look at. Some of those problems will be deemed essential and you should do them, and I'll be grading them. Others will just be there for your interest. Last thought is, oftentimes with with a book like this that's designed to be written for an exposure to proofs, you may feel an impulse to look at an exercise and declare that that exercise is trivial or it's easy or you know what to do, and it's what can I say? It's all so simple. I want to ask you to resist the urge to just gloss over things. If I point out a problem for you that I think is worth writing about in the homework, even if I'm not going to grade it, you should at least take some time to internalize what it is that I'm asking you to prove. So, for example, in the text, Axler proves that for real numbers, alpha plus beta equals beta plus alpha. Okay, I don't think he proves this. For real numbers, he assumes this. But he also proves this in Rn. But then in the exercises, example 1 asks us to change it from Rn to C. And so one might feel this urge to say, well, didn't he already prove this? Don't I already know this for real numbers? How is it different? That's an excellent question. How is it different? For complex numbers, all of these things are not real numbers, but they have these i's running around. And so in order to check this, you have to show that your familiar real number intuition works just fine when applied to these complex numbers that have both real and imaginary parts. And so this may involve going back into the text or looking for familiar properties. For example, maybe one knows something about how complex arithmetic already works from the discussion we had at the beginning of the video. Well, then one can maybe turn the right side into the left side by using properties for real numbers. It's important to know that it's not just an automatic thing. For example, if this is a plus bi and this is c plus di, then we defined this addition to be a plus c. Oops, sorry about that. Super sorry about that. A plus c plus b plus di. Over here, it's different, but now notice that because this is our definition, that's what this colon means, these being ordinary real numbers, I can commute them. Same with these guys. I can commute this to c plus a plus d plus bi, and that is by definition the same thing as c plus di plus a plus bi, which is beta plus alpha. But you notice it's not just a thing that happens automatically. Every step of my proof is either a definition or is justified from facts about R. And so as you are looking over these problems, I encourage you guys to keep this in mind, because as we are learning to shift our mathematical focus from computation to general properties of abstract vector spaces, it will be very important that we always have our eye on what we are allowed to assume versus what it is that we have to prove. All right, I think I've said enough at this point, so we're going to call it here. We're going to pick up in the next section, section 1.b.